So go ahead, Tim. We're listening.
Now I switch to English. That's safe.
Okay.
So thank you very much again for the invitation. And so if you have questions, please interrupt me. You can also write it in the chat, but also feel free to ask your questions in Spanish. I mean, my Spanish is still rudimentary, but I think it's going to work out. So thanks for coming and thanks for the invitation. So I want to talk about a project that I did together with my PhD student, Jona Lelmi. He's a very talented student at Bonn, originally from Italy, where he did his bachelor's in Florence and then moved to Bonn for the master's. And we were lucky that he stayed with us and started his PhD with me now 1.5 years ago. And right now he's doing a long-term stay at UCLA. And you'll see during the course of the talk why he chose to go to UCLA, because there's lots of connections to them. And well, so I chose this topic because it's actually quite nice, because this touches on several subjects. It's not too difficult, in fact, I would say. There are some technical details, but I will I will not show those. But it's difficult, but it's you have to combine things from different areas. So that's kind of also the beauty of this topic, that it's kind of you have to go into several areas. So okay, so let's so together with Jona, we did this work, finished this last year, but we have a follow-up project that we're working on right now. So this is in some sense still a work in progress, because it's also kind of new to me, this data science applications of calculus of variations. But yeah, well, so this is also the first time that I talk about this. So let's see how far we get. Okay, so let me first give you a very rudimentary explanation of what data clustering is. So this is kind of my explanation. I don't know if this is too mathematical or too simply oversimplified, but probably it's for my understanding, this is the essence of it. So you think of data points just as points in Rn in some Euclidean space, and so here each of these points is a data point. They're very thick because I want to color them. So I want to color them in different colors so that kind of we see what are the clusters, what are kind of the points that are close to each other, which ones don't have much to do with each other, which of these are far away from each other. So okay, I mean, this is a two-dimensional example. It's an R2, and we can all see that there seem to be 3 clusters, right? I color them here in 3 colors. But we want, of course, to do this in high dimensions, and we want then we can't just look at it and decide, and we would like to find good numerical algorithms to do this. So my my contribution to that area is to do analysis of these things, and kind of to try to understand, when you have large graphs, what is actually the continuum limit of these algorithms, which also helps you give new insights into algorithms and maybe design new ones. So it's not only kind of it's not only proving theorems, but it's also about getting new insights on algorithms and maybe designing new ones. So so what is the approach that we want to take here in this talk is graph-based learning. That means so I have these data points given to me, and I just know basically their pairwise distances. But I could also now construct from this a graph. So for each, so the points that I have, the data points, they are the nodes of the graph, and then I put edges, and maybe I put different weights. And now you see kind of when I want to kind of cluster this, you see already that maybe I want to cut certain edges and maybe not cut too many. So this is maybe another way to formulate it in this problem. And so let me give you a kind of very slow introduction of what I mean when I talk about graphs, and then we'll see what the actual algorithm is that I want to discuss. So so maybe I have to move this over. Okay. Okay. So what I showed you on the last screen was the similarity graph of given data points. So So here, these given data points, those were the big dots. And basically, in the first place, I just know the pairwise distances, but I can, when I want to kind of cluster things, maybe it's useful to collect all of these together. And now I have a graph with weights, and maybe the weight of each edge depends in some manner on the distance. So here are three very famous choices, and that just means that the further they are away, the smaller the weight of an edge would be. And maybe I can discuss this the simple example where you just choose, well, if they are further away than, let's say, 1, then you don't put an edge. But if they're closer than 1, you put an edge between them. So these two would be connected, but this guy is too far away from everything. There will be no connection. This is what I did in the previous slide, but just, I mean, I did this by hand, so it's probably not exactly correct. So once you have this graph, you can do some basic graph theory. You can define the most central object in graph theory, the graph Laplacian. And it's just this matrix here. And but I'm a PDE person, so for me this is some version of a Laplacian. So I'm happy that it has this this nice structure of being the divergence of the gradient, and we always want this to be a non-negative operator, so it's minus the divergence of the gradient. And oh, I think somebody's not muted.
Mario, ¿puede apagar el micrófono, por favor?
I think the host can mute. Okay, all right. Okay, let me go back. So you can define the graph Laplacian. So this is some very basic graph theory. And so you use the weight matrix where you collect all the different weights between different nodes. And you have to kind of rescale it by this diagonal matrix where you put on each entry here the inverse, because you're taking the inverse matrix 1 over the degree of that node. Okay, so and the nice thing is this Laplace operator is just like the Laplace operator that we know from PDE theory. It's self-adjoint. It's with this sign convention non-negative, and it has this nice form that is a divergence of the gradient. And the precise setting of, I mean, so there's lots of different graphs you can work with. So I want to work in a very precise setting because then I want to prove also something about those graphs. And the precise setting that I want to use is the manifold assumption, which means that we assume that kind of the data that we have, well, while it lives in this gigantic dimensional space RD, so D, you should think of a very large number. I'll give you an example on the next slide. There's some submanifold of much lower dimension. So I call this K. And this, basically all the data is just on this manifold. Well, if you want to be very precise, maybe it's also just close to that manifold, but I'm not going to consider this in this talk. So suppose it's on this manifold, and we assume that the data points are IRD random variables that are distributed according to some probability measure on this manifold, let's say with a positive, strictly positive density. Okay, so this is some smooth closed surface. So take, for example, the sphere, and we have some probability distribution that doesn't have to be uniform, and that is how our data is distributed. So often people work somehow in this setting, but they don't work really on a submanifold, but then just on the flat case. But we really wanted to know the whole story, so we worked on so there is some manifold. So this is really what people would have in mind in kind of theoretical computer science. And then we scale the graphs in the sense that we kind of we put some scale epsilon, some length scale here, and we rescale kind of distances. We want to compare them to epsilon, And that means also the graph Laplacian we want to, so there's like taken two derivatives, so we should divide by epsilon squared, so by the squared length scale. So that's the setup. And so here's, for example, this is one famous example of this, the MNIST data set. So that's handwritten digits, and you take images of these. So this is 28 by 28 pixels. So each point in our graph is one of these images. So here's one part of the graph. So there's just the ones and the threes, and each point in the graph is one of these images. So they live in, well, r to the 28 times 28. So that's basically r to the 1000. And that's a very simple example, right? If you think of larger pictures, colored pictures, where you have where you want to understand, is this a cat or a dog? Well, that's much more complicated. The resolution really changes the dimension drastically. So you have this gigantic dimensional space. But in principle, if you just do a very simple pre-processing principal component analysis, you just look kind of in which the two directions are, or let's say, first you look in which direction is this data spread the most, and then you look at the orthogonal directions, what is the next to most spread direction, and then you can get already a nice picture here, just with two dimensions. And that's kind of the essence of this manifold assumption, that kind of there's just a few parameters that actually play a role, but you don't see them in this, if you just write it down like this in a 1000 dimensional space, right? Okay, and here's, if you give me such a graph and I had to cluster it, well, I would start with the first guess, maybe, and then I would refine that guess. And this is the scheme that I would use, just because it's my famous scheme for doing anything. So it's the MBO scheme. So it's called MBO because it's originally due to this group around Stan Osher from UCLA. But then in this graph, so that was in the continuum setting, but Bertozzi and co-authors, they kind of wrote down this completely analogous scheme on graphs. So the only thing that you need to know is you need to know what the graph Laplacian is, and then you can run the scheme, because with the graph Laplacian you can solve the heat equation, the diffusion equation. So you can so I mean, maybe I'm not going to talk too much about how you would do this numerically, because that's also some issue, because a large graph, maybe you don't really want to compute this matrix. But for us in the analysis, maybe first it's just the matrix exponential that you want to take here, right? And then you apply this matrix to the vector that has ones inside your domain and zeros outside. So let's say we do this for this example down here. Let's say we put, for the purple points, we put a 1, and for the yellow ones a 0. And then we do the following. So this is our first guess that you can do with a very rough scheme, so that we did this with k-means. So my student Jona, he did this. This is the famous 2 moons example. So you want your algorithm to see that there are 2 clusters, but they are kind of intertwined. So you have to be careful. You have to find you can't just do a linear cut, right? So you have to be a little bit smarter than that. And let's see if the scheme does it. So you start with this initial guess, and then you just you kind of iterate the following thing. You just alternate between those 2 steps. So first you do this diffusion. So you apply this diffusion matrix to the vector, that it has 1s here, 0s here, and then, well, you have kind of, you don't have labels 0 and 1 anymore, but the labels would be something diffused between 0 and 1, right? So all these values are going to be some numbers between 0 and 1. So it's not really decided, is it yellow or is it purple? It's something in between. It's a mix. So, and then you kind of turn this into just 2 clusters again by saying, well, okay, so we took 0 and 1, so 1/2 is exactly the middle. At the middle, you make a cut. Everybody who has a convolution value, or this phi value here, larger than 1/2, which was the average of the two guys, larger than this, we put 1. Otherwise, we put 0. In other words, we put the purple ones where we color everything purple where the value was larger than 1/2. So here's here 3 iterations. So you start with this initial guess, which is just putting a hyperplane here. And you see it's getting better and better. And this is already an acceptable outcome somehow. Okay, so you see that they're really, so the algorithm saw that there are 2 clusters.
Sorry, Tim. What is the stopping rule of that algorithm?
Oh, excellent question. So in practice, what people do is they just run 3 or 4 steps, right? So in principle, for me as an analyst, you basically run it until you can't anymore, right? I mean, so at some point it's not going to move anymore. You don't want to run so long. But for me as an analyst, I'm thinking of, actually I'm doing time to infinity. So, but as you arrive here and you do 1 more step, maybe it's going to change a little bit, and then you want to stop. So you should add some rule when you stop. What people do in practice often, they just do actually 3-4 iterations. They don't even and then they check the outcome. But you could also of course put kind of a smarter rule where you say, if you haven't moved more than this and this, because you can of course count how many nodes changed their color. And you see there's a considerable amount here and here as well. From here to there, not so much anymore. So you could, for example, take this, right? So you can take this as a stopping criterion. Okay. So if less than 10% of the nodes are changing their color, then we stop.
Okay, thank you.
But it's an excellent question. So I haven't investigated this. What happens if you actually do stop earlier? Because I'm kind of so this is the first analysis on this scheme, and what we do is kind of a very idealized situation that I think you do infinitely many iterations. I mean, you don't have to do infinitely many, right? And it's just kind of something that depends on the number of points, but really lots of iterations so that you really stop moving, which you would never do. And that is the state I want to analyze. But actually, that's what you're interested in, right? Do enough iterations so that kind of it's almost not moving anymore. Yeah, excellent question. I mean, there's probably a smarter way to come up with a stopping rule, but yeah. So I'm kind of idealizing the situation for me that I run it until nothing moves anymore. So let me change to the next slide, which is almost the same. Just to convince you that, well, you can do the same if you have more than 2 clusters. So I just showed you everything with 2 clusters. So there's yellow and purple, and I didn't change the pictures here just so that the slides really look the same. But I just want to convince you that it's really the same. So you have P clusters, let's say. I always use the letter P because it's like the number of phases. Kind of if you think of several fluids, for example, this would be the number of phases. And there's so many letters that I had to, use a different letter. So P is always this one. And we're going to forget about this in a moment. I just want to convince you that you can actually do this. There's no big change because you just, for each of these, so you would do one for yellow, one for purple, and then one for the next color that you have and so on. Like the first graph that we had, you would do one of these vectors would correspond to ones in the red, for the red points and zeros for all the others. And then the other one has ones exactly and the blue ones and so on. So you have to do this P times. So for each of these clusters, you have to do it once, and then kind of this thresholding step becomes kind of a winner takes it all. So at any point, you check who has the largest value for these outcomes of the diffusion, and that phase claims that point. And yeah, okay. So the scheme is then just as efficient as before. Okay, it's kind of, if you have P phases, you have to work P times more, but then you can also do some tricks by combining phases and so on. I don't want to go into these details, but just that you know, it's not just two labels, because I had this example with 3 labels and with 3 clusters that I want to find. You can put this in, but you have to put this information in at the beginning. At least you have to put an upper bound. You can say, okay, at most there's going to be 100 clusters, and then you can run this, and it's going to tell you, oh, there were actually 5, and that is the outcome. Okay, So, but I want to come to the analysis. But let's first let me first show you one more slide on the scheme, because I want to show you also the original scheme from the 90s that was due to Merriman Benz and Stan Osha, which is very nice, but it has more. I mean, kind of the goal is a very different one. So it's really the same. So you do convolution, or you're solving the heat equation. And then you're taking a super level set. So you're doing exactly the same thing. So now I'm thinking of the continuum case, right? So you have some subset omega of your R2 in this case, and then you diffuse this characteristic function and you take a super level set again. So you kind of, you're just changing sets. And the interesting thing is that, I mean, so why they came up with this scheme is because they wanted to find an efficient algorithm to simulate mean curvature flow, which is a very famous geometric evolution equation that I'm also very interested in. And there's several proofs that show that this converges to mean curvature flow in some sense. And you see in the numbers that there's a huge gap in the years, and that is because those are very different methods. So these old papers by Greg Evans and then other people in the 90s, they're based on the maximum principle, kind of viscosity solutions, and the maximum principle. And these later papers by myself and Felix Otto, and by myself and also Jona, so he started with this continuum case, and then we went to the data case. So there we don't use this maximum principle, but we kind of, our proof relies on the gradient flow structure that I want to explain you in a moment. So that's why there's a large gap in the literature, because those are very, very different methods. So, and what's the benefit of using the second kind of sets of methods? It's because it's not kind of constraining you to just having two labels in our previous case, or here just two phases. So, because, I mean, this is very interesting for mean curvature flow, because that models some process in polycrystals where you have lots of grains that grow over time, and what you can do with these methods back here is you can understand what happens if you have one grain inside a much larger grain. But what you're actually interested in is very complicated kind of networks of grain boundaries, and then you have to come up with very different methods, and that's why kind of it's legitimate to kind of come back to these problems and study them again from a different viewpoint. And just like the methods here, also in this talk, I will talk about the second approach, which is kind of really like calculus of iterations. There's an energy functional, and we want to understand that. Whereas, so I want to point this out once more here, you're really interested in the dynamics. So you really want to understand what's the change of these things. Whereas in the example of this data classification, not classification, clusters, I mean, that I want to find clusters, I'm not interested in kind of how did I get here. I'm mostly interested in this last iteration. I'm not interested in how did it move from here to there. So that's one of the main differences between these two applications. But let me tell you a little bit about this viewpoint of looking at gradient flows. So gradient flow is the steepest descent in an energy landscape. That means that so here I'm writing it down just like an ODE. So chi will be this kind of the clustering, kind of this characteristic function that gives me the ones and the zeros. So abstractly speaking, it's an equation like this. So you have I give you an ODE basically. So time derivative of chi is some right-hand side, and this right-hand side has the form that it's the negative gradient of some function, and this gradient I compute with respect to this Riemannian metric that I have. So one very important thing that I want to record here that we will use in a moment is that any such gradient flow comes with a very natural time discretization, which is called minimizing movements, where kind of you discretize time just like we did in the scheme in this continuum scheme. And in each step, you look for a minimizer of a variational problem. So you solve a variational problem. So you're looking for a minimizer of this energy plus squared distance. Okay, and why would you do this? I mean, if you just do this in the Euclidean case, if this is the norm of the difference and you just compute the Euler-Lagrange equation, this is just exactly the implicit Euler scheme. So it's some version of the implicit Euler scheme in some sense. So let me run this for this energy up here, where let's say we start with chi0 down there. So what I have to do is I have to compute the gradient. So that means I compute the derivative. That gives me the slope, and then I compute kind of what's the gradient, and I take the negative gradient. So it's going to point to the left, and you're going to move kind of proportional to h times this gradient. In this case, that was to the left, and you compute again and again and again. And what you're doing is you're moving to the left all the way to this minimum, right? And just like in the scheme that I showed you, you're kind of getting closer and closer to some optimal solution, but kind of you're not really reaching it. You're getting closer and closer, right, over time. There should be also here some stopping rule, maybe, if you want to do this as a numerical algorithm. But also one thing that you see here, well, you will run into a local minimum, not necessarily into the global minimum. That depends on your initial conditions. And in these data science applications, there's lots of local minima. And what we want to understand is, well, what's happening to these local minima in the energy landscape? So, but what is the energy? And that is some observation by Selim Eziloglu and Felix Otto from 2015. So it actually was a little bit earlier. So this was the first reference. And then this group around Andrea Bertozzi, they kind of used exactly this and said, okay, you can do the same. By the way, you can do the same on a graph. So the idea is actually from here, from the continuum case, but you can do the same on a graph. And it's this simple observation that, well, this MBO scheme, kind of, you do solve the diffusion equation and then do thresholding, is equivalent to solving a minimization problem. And that's quite, I mean, it's quite remarkable because, I mean, there was no minimization problem, right? There was an explicit kind of rule what to do. You do this kind of, you multiply with this matrix, and then you take kind of, put a 1 if it was larger than 1/2 and a 0 otherwise. But it's the same as this because, I mean, this simple two-step scheme you can write down as a linear, as the solution of a linear minimization problem. And here you kind of just expanding squares. So kind of this is a quadratic form, right, in chi and 1 minus chi here. And you kind of expanding, you're adding the square if you kind of compute if you expand the square, kind of the quadratic term cancels, and you end up with this linear function. And so what I want to focus on in this talk is just the energy. So there's some extra term here, and it has this minus sign there, but it's, trust me, this is a positive term, and this actually, it behaves like a squared distance, just like before. So we'll ignore this term, and we'll just look at the energy. So, and this energy is it's very intriguing, and it's also has been known for a long time, this heat content energy, which tells you, okay, if you start with a heat distribution that is 1 inside your 1 cluster and 0 outside, then you let the heat evolve. So kind of the temperature, I mean, the temperature is going to go down because the heat kind of can also escape to the other nodes. And then you actually going to compute what is the total heat by computing the scalar product. What is the total heat that escaped into the complement? And that is proportional to kind of what surface area there is in between, roughly speaking. And that is what we want to make precise. So what we want to understand is when you have lots of data, so when n, this number of data points, goes to infinity, how does this effectively behave? So actually what you would like to understand is if you take n to infinity, epsilon to 0, and h to 0, what is the limit? this is a very ambitious goal because there's very complicated processes. Kind of the details of the actual graph can matter, and it's also known that I mean, analytically, but also numerically, you observe this, of course, that if for example you fix epsilon and you take h too small, then you're going to get pinned. You're not going to move at all because there was not enough diffusion to kind of get to the next node. So you have to kind of choose your parameters smart, in a smart way, and our analysis kind of goes the first analysis goes the very extreme way that we first take n to infinity and epsilon at a certain rate to 0, and only in the second step we take the time step size to 0. In some sense, maybe you're also not too much interested in very small time steps compared to epsilon because, well, I mean, you just want to kind of you also want things to move, right? So the time step here gives you a certain kind of resolution because it's kind of making the transition sharper here, but it's not, maybe you don't want to take it too small. So that's why it's kind of natural to first take this limit and then this limit. Well, if you did it the other way around, it would become trivial because of the spinning. So you could do a joint limit, but that is a very delicate problem. Okay, so I'm going to show you these two results, the two main results we have in our paper. And so the large data limit is the first one. And it says that kind of the effective energy, so the limit of these energies in a certain sense, I will tell you what this means, the sense of gamma convergence. So these energies converge to some effective energy, which is this one here. It has a similar form, so it's also, so you have some diffusion operator acting on u. You take the scalar product with 1 minus u, and the scalar product is in this weighted, with this weighted volume form on your manifold. And the prefactor 1 over square root h, well, this didn't change, right? That was there the whole time. So this kappa, this diffusion coefficient is just some number that depends on the exact, I mean, not the exact shape, but some properties of the cutoff function that we used. So this eta that you use to kind of compute the edge weights. So it's just kind of the quotient between the second moment and the 0th moment. So the second moment and the mass. So it's just some number, and from now on it's going to be equal to 1. Okay, so it's just a number. And the interesting thing is, of course, what is the operator here? And that is the Laplacian on the weighted manifold, which is also of this form divergence of gradient, but it's kind of on this. So I'm hiding kind of the dependence on the metric, but I'm kind of pointing out what's the dependence on the density. Okay, so that's the first result, which tells you that these energies converge to a nice energy. And that is in some scaling regime, which is kind of linking the length scale epsilon, which would be the distance that if you're smaller than epsilon, then you would put an edge, and if not, and I mean, if you're much further away, then you would not put an edge there. And kind of this has to be sufficiently large compared to the average distance that you would expect between points.
Sorry, Tim. I have a question. So is the density is like some explicit function, or I mean, like
excuse me?
Is the density an explicit function? Does it depend on the manifold alone, or
okay. Oh, sorry. Yeah. So this density rho was fixed in the beginning. So this is
okay.
So I fixed from the very beginning. You remember I had this. So we have the standing assumption that I should write this down. Let me write it down here in blue. So we have these points xi that are the nodes of the graph. They are distributed according to some probability measure. And I should have repeated it here. So this is some density times the volume form on M.
Okay.
So this is my standing assumption. So this is given to me. So I give this and I get this out here. It is quite funny. When I did this the first time, I was a little bit surprised, but there's no news in that community. You start with rho times the volume form, and you end up with rho squared times the volume form. And that, right? I mean, you choose them according to this probability measure, and what comes out here is kind of this rho squared, which comes from the fact that kind of these scalar products that you always compute on the graph, they're like double sums. It's kind of like so there's kind of there's two integrals. That's why you get rho squared, and they kind of collapse to one in this case here. But that's why you get rho squared. I was first surprised to see rho squared, but then my student Jona told me, well, it's not so surprising. Okay. So, but it's you put this into the this is part of this is the standing assumption, this manifold assumption, which is that there is this density, and a crucial assumption is that this rho is strictly positive. Okay. Any other questions?
Yeah, that's fine. Thanks. Yeah,
okay, thanks. Is there any, I mean, maybe that's a good point to also ask other questions if there are more questions. Okay, so this is kind of the setup. This is the result. But that's the first one. Okay, now I'm going to show you the second one, and then we can go into the gory details. I will also show you what I mean by this convergence here, because it should tell me something about the convergence of minimizers. So I'm doing the scheme, and in an idealized world, I'm going to end up with a local minimizer of this energy. And I want to know, do local minimizers of this, how do they look? And I claim that this result here, just this plus some abstract nonsense, tells you that these local minimizers actually look like more local minimizers of this function. But then your next question could be, well, this is a funny integral that I have to compute here, and there's the heat operator. I don't even know what this heat operator is, right? Right? I know what the Laplacian is, but now I have to take I mean, this is no matrix exponential anymore, right? This is really solving the heat equation on the manifold. That is quite complicated. And so how do minimizers of this look like? And that is the next theorem, which I find the more challenging one, but it's kind of well motivated from this data science perspective, that you try to understand, well, how do minimizers of these guys look like? And so that is given by kind of the gamma limit. I'm going to tell you what this is in a moment, I promise. And the effective energy that you actually have there is a very simple one. It's just kind of so this is some kind of total variation norm of the gradient of chi, which if you have some regularity, so formally, so if you have some regularity, you can write it just as a surface integral. So let me draw a picture. So here's a patch of your manifold, let's say. Okay. So this is a patch of M, and what chi is doing, chi is coloring some of the points yellow and some of the points purple, right? So it's going to be lots of yellow and lots of purple. So that's what the scheme did earlier, and it's also going to do this here. So just that now this is in the continuum case. So it's really a continuous, and it's on this manifold M, and what this would be maybe chi equal to 1 like before, and this would be chi equal to 0. Maybe it was the other way around. And what this energy is computing is the surface area of the interface. So in this case, I'm drawing a two-dimensional picture. So it's the length of this line. Let me draw a red line between them, the length of this line. So in general, so you have some given manifold M with some weight, right? This rho, but you can, it's already interesting that if rho is just equal to 1. So you have a manifold of volume 1, then the constant 1 gives you a probability measure. And what this is saying, that if you look at kind of outcomes of the MBO scheme, well, you get from this strange energy, you get to this intermediate energy, which is lives on the continuum, but still has this non-locality through this parameter h, because you have to solve this diffusion equation. But effectively what you're solving is finding a minimal surface that cuts your manifold into two parts, right? So find a minimal surface. So it's kind of interesting that this very simple scheme, right? I mean, kind of computationally simple, that kind of you solve the heat equation and you do this super level set, that this gives you, that this kind of actually is doing the right thing on the graph, because it's kind of trying to find surfaces that have least area. So, and kind of that's what we were trying to do, right? It's kind of giving you some consistency of this scheme, that kind of what it's doing is it's trying to minimize the area of the cut that you have to make in order to cut it into several clusters, your whole data set. Okay, so this is the two results. And okay, let me put them on one slide again, so without any gory detail. So the first theorem was the large data limit, so that is n to infinity and this epsilon n to 0. So that is this first limit. And the second theorem, we went down here and took the sharp interface limit, or in some sense you could also say this is non-local to local, because this is, you still have to solve some equation and then kind of compute some integral, but once you get here, there's no extra PDE that you have to solve. This is really a local object, and solutions of this are just minimal surfaces. Minimal surfaces have this nice property that the mean curvature is equal to 0. So it's a local statement, right? If you look for minimizers of this, there's going to be some weird convolution operator or some strange, I mean, take the solution of the heat equation and it has to satisfy this and this. So it's very implicit. And here, in this case, it's something very explicit. It's the mean curvature is 0. If you give me a surface, maybe I'm going to have a hard time computing what the mean curvature is, but in principle, I can do it. I can look at it and just say it. Okay, so that's the two results. And maybe let me give you a couple of comments on how general they are, because of course I didn't show you the full results. So you can take any number of labels or number of clusters. I should say. So this is not labeling. So I should say clusters. So this number p can be any number. Oh well, label is fine, I guess. But so this number p that we had earlier, you can take any number, but I'm not going to show you the formulas for this. And you can put some parameters there. You can kind of put different surface tensions between different labels. You could say, for example, well, I want to pay attention that the 1s and the 7s, which look very similar, that I pay very much attention to distinguish them, and so I put a very large, I put a very high price to pay if I cut between those. So this is something that now you can kind of nicely incorporate here. And this is something that comes from the analysis that you know that kind of for minimal surfaces you can put surface tensions there, and then you can also do this for the scheme. And you can also put some drift term there, which is just changing. I mean, so in the algorithm, this just means you change the threshold value, kind of this from 1/2 to this value here, which should be proportional to square root h. So you just change it a little bit. So it's proportional to square root h, but also proportional to the forcing that you would like to have, the drift. And it's quite interesting that then the energy also just changes by some nice linear function. And so analytically, it's very simple to analyze this. So we can also do this. And you can also do other variants of graph Laplacian. So it's not only for the random walk graph Laplacian. Okay, now let me, so now I'm going to go into some gory details. So I hope I have enough time to do these things. But so I'm going to start with something. I'll do this rather quickly, but it's something very basic. And I think if you haven't seen this, it's worth looking it up in a book again. So
Sorry.
Yeah.
I have one question, maybe before you continue. So if I remember correctly, most of this is based in the algorithms by the MBO algorithm and the Bertozzi algorithm, which are based on the evolution by the heat equation. Is there, I mean, like, would you expect to obtain something different if you change the operator, or I mean, like, or is there any other, like, I mean, like, of course the heat operator is a very nice operator, but I mean, like, would you get something different if you replace it by something else, or is there any other?
Yeah, that's an excellent question. So so first of all, so I the hardest time I would have is to come up with good operators that do the right job. So if you tell me this in the continuum on Rn or even on a manifold, I can tell you what kind of operators you want to take. And what you usually want to do is you want to write down a kernel. So usually, what we do in the continuum case, so this is a very good question. So in the continuum case, you would write these things. Let me write it down like this. So you have this, you would write down this energy, and I would write it down in terms of the heat kernel. So this is a convolution with a heat kernel, and that's just a Gaussian. But then nobody tells me that I should take the heat kernel. Actually, I could take any other kernel that is nice. And that is a very very tempting proposition that you have, that you take different operators. And so on a graph, what I would do is, so there's one nice, so our results don't apply to this. Our results just apply to the heat operator, really, exactly the heat operator for now. But I know that so in the continuum case, there's lots of results also if you look at different kernels here. But somehow the big difference between what we do here and what's being done on in the Euclidean case is that we don't have such specific information on the kernel. If you have a nice kernel, then this is actually very easy to show that this converges to the right thing. This is continuum but non-local, then it's actually not too bad just to understand that these energies converge. So you would say, okay, let's not take the heat kernel, but give me any kernel k, and then I have to rescale it. So I take so I have some shape k1, and I just rescale things with square root h, and then the dimension. So I just kind of take some kernel, and then I can do this. And so what's interesting is if you put some anisotropic kernel, I mean, you could take rotationally symmetric kernels and then you get the same equation. You could, but you could also take kernels that depend on the direction, kind of where different directions get have a different shape if you go down that direction. And then you get anisotropic versions of the parameter. So you don't get the integral of 1 or rho dHd minus 1. But you get, so you don't get this here, but you would get, so you won't get this, let's say, but you, instead of this, you would get the following. You would get some function of the normal. So different inclinations have a different cost. So it's like these surface tensions where a different interface between two different phases. I mean, the energy per unit area would depend on the labels. Here, it would also depend on kind of at which angle it stays to some reference configuration. So this you would get if you had a kernel k that is not rotationally symmetric on Rn now. So now if you're on a graph, so what you would do in the kind of from a numerical point of view, you would not compute the matrix exponential, but you would actually just do maybe some compute some powers and then use this, right? And that is a good question. What happens then? So so we don't know this yet, but that's something that's definitely a good question. I've already been asked this by some friends also. That's a very good question. So our result only works for exactly the heat equation at the moment.
Sorry, and maybe one last question. Like, which point in your proof depends exactly on the thing being the heat equation? Is it like the gamma convergence or one of those results? Or?
Yeah, I'll show you. I mean, we'll go through the proof. I mean, there's several points where it depends on that.
Okay.
So I guess if you want to extend the proof, probably the best thing to do is change the equation a bit, but still have a PDE. So we really use the PDE instead of. So what's been done earlier is always that you use a kernel, that you actually have some non-local energy where you kind of have some convolution interval. But what we do is we actually use the PDE instead. So you will see that it's going to show up a bit, and then so that's yeah, I'll show you. Okay, so but before that, let me tell you just what this gamma convergence means that I meant there, and that I mentioned. And so this is abstract nonsense. This is just it's very beautiful but abstract theory that just applies. And okay, I'm writing down this in a metric space. You can also do this in topological spaces. And it's the following. It's kind of a notion of convergences for energies, just like we like in our setting, we have some energy that depends on some parameters. Here it just depends on one parameter for simplicity. Right, and all the others are fixed in that moment, and you want to understand what does it mean that they converge to this energy, and here's the definition. It's not a pointwise conversion. It's not for every configuration it converges, but there's two parts to it, and it's a little bit for those in probability theory. It's a little bit like large deviations. You have to prove two inequalities actually, and the first one is a general lower bound. So whenever you have a sequence that converges with respect to this metric, could also be in a topological space, then it converges with respect to this topology, then you have to maybe put some more assumptions here. But for any sequence that converges, you need to know that the energies are bounded below by the energy of the limit. So this is a lower bound on these energies that applies to any sequence. And then the second item is an ansatz for an upper bound. So that means you have one particular very smart, so maybe I should give this here a different name. It's called as U bar. So there's a very smart for each configuration X, you can find at least one smart choice of such a sequence. And that's called the recovery sequence because it recovers the correct number here. I mean, the number that comes out here as a lower bound is here the upper bound. That means that this lim sup is actually a limit, so the energy is actually converged to the correct number. So this is an abstract definition. You can just take this for granted if you want to. The nice thing about this, so let me put the bars here again. The nice thing about this is that, and this is why people work with this setting, is that this is a sufficient condition that local minimizers will converge to local minimizers. So if you have if you know that you have gamma convergence and you have a sequence of local minimizers, and you know that they converge to something in this metric space. So here I wrote it down for topological space, should be a metric. Then this limit is a local minimizer. So that means that that I know how these minimizers look effectively. If the parameter n is large, they look like some minimizer, okay, of this energy E. So this is a very powerful tool, and well, this has been around for a long time. Is basically due to De Giorgi and co-authors, and so this is a very, very common tool in analysis. But it's also, as you see, if you're in probability theory, somehow it has some similarities with large deviations. And so this is why we wanted to prove these theorems that we had before, because then this meta theorem here, this very general theorem, tells us, well, the outcomes of thresholding when I do long enough in my idealized situation that I actually arrive at a local minimizer, doesn't even have to be a local minimizer. It could also be a saddle point, right? If I run a gradient flow long enough. So with a grain of salt, I arrive at a local minimizer. And what I know is that this local minimizer, if the graph is large enough, is similar to, it's very close to a local minimizer of these other energies. First, it's close to some local minimizer of this non-local energy where you still have the heat operator in there. But this thing in turn is close to a local minimizer of just the area functional, so just a minimal surface. Okay, and then maybe just one word on this metric that, so I didn't write L2, but TL2, and this T stands for transport. So the problem is that if I want to apply the theory from the slide before, well, it's a little bit of a problem because the UN lives on the graph and U lives on the manifold. So they don't live on in the same space. And there's a very simple, but very helpful tool. And this is using optimal transport. And in this simple case that we have here, so this is not the definition, that's, but if you have this nice transport map that we have, it's just saying something about the composition with this transport map. So maybe let me draw a picture again. So we have this nice manifold, but then we have our data points that are somehow distributed on this manifold. And this plan, or this transport map T, tells me, it kind of gives me a partition. It's a little bit, maybe reminiscent of what you that maybe looks like this, and that's it. Reminiscent to a Voronoi tessellation, that everything here maybe is mapped to this point, everything in this cell is mapped to this point. So it kind of tells you who is mapped where, and kind of it's a map from this manifold, this continuum object, to just these finitely many points. Well, it's not the Voronoi construction, but it's kind of, if I draw the picture, it looks like this, right? This is what this transport map is doing. And of course, then I can pre-compose with this, and I have a map that lives on the manifold, because I plug in a point from the manifold. This will be somehow projected onto one point on the graph, and that, of course, I can plug into my function that only lives on the graph. So this has been known for kind of when you look at strong convergence in this space, and that you can do, for example, if you look at the Dirichlet energy, or kind of energies that have kind of some gradients in them. But here we don't have any gradients, and kind of there's no regularity that we get. So we have to work with weak convergence, and then okay, so we just define this to weak TL2 convergence by saying that kind of these compositions, they converge weakly in L2. And this is also the space in which you get compactness. So this is exactly what you would like to have. And now I'm going to actually tell you a little bit about the proofs. So for the first theorem, the large data limit, we have the following proposition that tells us something that you might expect, but I haven't seen it written down anywhere, that if you have a sequence that converges weakly, so UN just converges weakly, then, and you let the heat equation flow for some fixed time t, then the outcomes of this, they will converge strongly. Just like on Rn, if you apply the heat operator to something, it mollifies things, it makes things nicer, and it turns weak convergence into strong convergence. This was not true, not completely clear to us in the first place. It has to be true, but kind of you have to prove it, I guess, because kind of the operator that you convolve with here changes, right, with n. So kind of you have to be careful in doing this, but you can prove it. And the idea is basically that you pass to the limit here. You first find kind of a nice stable form of writing down what it means to be a solution of this. And we do this by something that we learned from gradient flows, that kind of gradient flows are characterized by this inequality, by such an inequality where you kind of just check how fast is the energy dissipated. And in this, you can pass to the limit by lower semi-continuity in all of the terms. That's a lot of work, but you can do it. And on the other hand, so this tells you can pass to the limit, but on the other hand, it tells you also, well, in addition, you also have some regularity because you have these extra estimates. And then, you can kind of, with this, you can prove that it converges to the correct thing, but also strongly. Okay, and then just as a simple corollary, we get that that for any sequence, just like here, any sequence that converges weakly, the energies converge to the right thing. That means it's much stronger than gamma convergence, what I stated in the first theorem. But the first theorem is kind of every sequence is like the recovery sequence in item number 2 of the gamma convergence. So every sequence is a good sequence in some sense. So it's much, much stronger than gamma convergence. But I mean, this is how you usually state it, because the important takeaway is that local minimizers converge to local minimizers. So, but now let's come to the kind of the challenging problem, and kind of you can take this as an excuse. So this data science problem to say, well, that's a good excuse to look at this very challenging problem that you have. Give me a manifold, and I look at this heat content, and I want to understand, does this converge to what I said before, this this weighted total variation norm. So first of all, if you're in the Euclidean setting, so there's several proofs that work there. So there's a proof by Alberti and Bellettini, Miranda, Pallara, Baronet, and Poincare, and Ezedoglu and Otto is the latest one, which are kind of all of them very pretty proofs that prove maybe, okay, so this work here from 2007 doesn't prove the gamma convergence, just the pointwise convergence. So there's a little bit less, but all of them anyways only work on the flat case, on kind of everything is translation invariant, and kind of it's not curved. So you're really on Rn with a constant density. And well, we have a varying density, but more importantly, our manifold is curved. So this is this is a very, very challenging problem. Actually, it was left open in this paper, and they announced a follow-up paper in which they only proved the convergence of this functional, which is, to be honest, much easier, because it's kind of, this is, if you look at this, this is already kind of a lower semi-continuous functional, and you're kind of just convolving here. Whereas up here, you are really changing the type of functional. So, yeah. So I should put, sorry, this is the first time I talk about this. There should be 1 over square root h and h here. There's a typo. So this there's a typo. So of course you compute this, but you rescale by this characteristic length scale. There's no prefactor here. That's correct. Okay. And okay, so there's these several proofs, and you can look at them and check which one applies. And of course, first of all, we looked at the most recent one by Ezedoglu and Otto, which is a beautiful proof because of its simplicity. And it depends on 2 things, monotonicity in the time step parameter and some disintegration method, which is kind of just you do slicing and then you reduce it to a 1-dimensional problem.
Sorry, Tim, we have 5 more minutes.
Yes, I'll get to the end. Okay, so this doesn't apply because, well, this relies first of all on kind of the precise form of the heat kernel in Rn. And on the other hand, you can actually numerically at least show that it's not true, that you don't have monotonicity, but you have so on Rn, the energy is just decreasing, and here it's increasing and then decreasing as you change the step size h. So there's a strange dependence on the step size. And also this work by Alberti Bellettini doesn't quite work. Okay, so I'm going to show you one computation that shows you that kind of the heat equation plays a role in our case. So I'm going to drop the indices here, the kind of density and everything here. But you do a very simple trick. You do the fundamental theorem of calculus. So I just compute what the energy is, and you do fundamental theorem of calculus, and then you compute what the heat operator is, and you put maybe the Laplacian. You put one gradient on the other side, and then you recognize that this integral here, and I swap the two integral signs, right? I mean, there's some Fubini theorem that I do here. Now the point is that this here is a surface integral actually, because I'm taking the gradient of a characteristic function that is really a measure actually. So I'm integrating over the interface. I'm integrating this function here, and this vector points in the normal direction then. And I divide and multiply by square root t, because now what I actually only need to show is this statement. Let's take this for a moment. Let's take this for granted, because if you plug this in, then you can compute the limit, and this integral here is equal to 1/2, and you get exactly the energy. If you only knew that this was true. Okay, so that's the whole computation basically. So you need this pointwise convergence, and it's a strange convergence, because it's not something convergence in some function space or so, but because you want pointwise that these things here converge, but you take the gradient of this thing, which is a horrible object, because as t becomes smaller, this converges just to a measure, and you can't evaluate this at a point. But you rescale with square root t to kind of tame the singularity, and it should you want to get out something that just points exactly in the normal direction. And here's a 1D sketch of how this profile should look like, and that it's kind of obvious that it's true, but it's actually this is maybe the main work that you put in here. And that is just kind of the recovery sequence, just the item number 2, the Ansatz-free lower bound, the general lower bound. Well, you have to work a little bit harder, and then you have to also use the blow-up method by Fonseca and Miller, but maybe I'm not going to talk about this. So here's the summary, and maybe I'm not going to read it out, but leave it at this. This is the paper if you want to download it and take a look. And thank you for your attention, and sorry for being slow.
Thanks a lot, Tim, for this talk. It was very, very interesting. And I don't know if someone has a question o cualquier pregunta. Tim también habla español, entonces también puede ahí responder. Any question?
I don't have any question, but I would like to say Teredos a very nice talk, and yeah, and so I mean, like, is this the first time that you do this kind of work with students, or I mean, like, do you also have like PhD students or any other? I mean, sorry, maybe the question would be like, how did you know your student was like proficient enough to embark on such a problem? I mean, like it doesn't seem. I mean, like it seems like a problem that demands a lot of like technical power. So your students should have been very well trained in order to embark. I mean, like, especially in the masters, for us, or maybe even like in US. You would not expect a master student to have like such a.
So Jona is a PhD student.
Okay.
Is a PhD student and is now 1.5 years into his PhD. But he's also very good. So I knew him from before. So he did his master's here in Bonn, he didn't write his master's thesis with me, but with my colleague Stefan Müller, who I also mentioned here. I mean, but this is just a coincidence. So he's so it's my senior colleague Stefan Müller, and well, I mean, so Jona is very good, and he attended a lecture of mine when he was a master's student. So I already realized that he was very good, and he wrote also a very nice master's thesis for which I was the second advisor. So then he applied for PhD positions, and then of course you have to write something in your application so you can tell if a person is kind of good. And then the first project he also did very fast, and then kind of we did this second project, which involves maybe even more different techniques, but kind of maybe the first project on a technical level was even more difficult. So kind of even the first project was difficult that I gave him. Yeah. Okay. But yeah, he's very good. Okay. Yeah. I mean, otherwise, yeah, I'm also advising at the moment for master students, and those are also not easy problems, but yeah, usually you can. So in Bonn, students are quite good, so you can give them quite difficult problems also. So then the problems are not as difficult as this one, of course, but they're not uninteresting, I would say, in the masters.
Okay, thank you, Daniel, for a question. Any other question? I have a couple of comments, but maybe if someone else has a question. So Tim, for the, I mean, when you define the graph, you assume some kind of correlation structure between the nodes. So I saw that you use exponential and also uniform correlation structure. So have you tried polynomial correlation structure? So that's or because of the Laplacian or the behavior of the Laplacian, you don't have that issue at all?
So these are just examples, these ones here. Mm-hmm. So this is so actually the proof holds for any. Okay, so now I have to be careful. Eta has to be decreasing, so it has to kind of qualitatively look like what I wrote down there. It should be decreasing. It should okay. So this one here is just kind of in the applications a nice example. So for us, it's decreasing and smooth. So it's actually a C2 or C3, I think. And it's decreasing, and you need second moment bounds. So it should kind of decrease fast enough to 0. But that's it. But I mean, then there's another thing which maybe you are more interested in, is that this. I mean, they're really IID for me.
Okay.
The points, how I choose them, right? I mean, kind of this is the probabilistic part where you kind of, I take the simplest. They're kind of really uncorrelated, right? So they're IID.
So yeah. But the graph can be correlated in some sense. I mean, the different points, they can be correlated spatially on the graph.
No, so I mean, okay. So let's say it like this. So the points, the nodes of the graph. So I take them as these given points in Rn, right? So the only probability is coming in here.
Oh,
that
okay.
I'm choosing randomly these points. And then the graph is by taking the first n points, just I mean, to make it a finite graph, I take just n of these points, and they're independent where they lie. Mm-hmm. And then I compute this deterministic function here.
Okay, I got it. Yeah. So it's not it's just a distance. It's like a distance idea between the nodes, but it's not the probabilistic behavior of the nodes in terms of correlation.
Exactly. This is not the correlation, but I mean, and they're completely the locations of the nodes are completely uncorrelated here. You could think of something more complicated here, but I mean, in order to get a geometric problem in the limit, in this large data limit, mm-hmm. I need to put in some geometry in here somehow. So somehow I need to kind of, in some sense, I can't just take an abstract graph. I can't just say, okay, I mean, I could also just take the numbers 1 to n, right? This is all I have somehow here. And then somehow take a random graph, because that doesn't give me a kind of a geometry that I would expect here in the limit in this. This is why I wrote down this precise setting very early, so that it's a kind of it's a very one narrow region in this graph theory business, right? So it's these graphs are coming from really this application.
Okay, I got it. So how difficult it is to, I mean, to consider some kind of graph that involves in time? I mean, so you can change the behavior, some kind of dynamic or something like that, and try to do the clustering with respect to time as well. I don't know, it's just an idea.
Yeah, this is an excellent question. So that's something I'm talking to my colleague Franka Hoffmann about also. So so in some sense, I mean, so there's lots of, so there's, let me start like this. So you have these points in space. Now you could do an equation for the points, right? So you could write down an evolution equation for them, and then maybe you do also gradient flow, and you have some potential that tells you where to go. But maybe you want to have this potential depend on kind of maybe the outcome of this thresholding, or somehow the outcome of whatever classification you have or clustering on the graph. So kind of not only on the geometry of where the points lie, but also kind of all the information you got from the graph structure, from kind of the graph Laplacian, or here with this diffusion equation, that you kind of say, well, these are red points and these are yellow points. And maybe I want to move the yellow points together and the red points together, but not, I mean, they shouldn't interact too much. And that's something we're trying at the moment also, to kind of come up with something that combines these two worlds of, I mean, there is a world of moving the points around, and there is a world of moving, kind of giving the points, deciding what are the colors that I should put on the points, or kind of what are the labels or the clusters. But combining these two is, of course, that's a very good question. And then maybe you want to alternate, and that's something we're starting to do now. But yeah, I'm also happy to talk about these things.
Because in that sense, you have to weaken a little bit the third assumption there. So you have to include something like kind of dependence on time or something like that. So I think it would be a very
exactly. Yeah,
interesting.
So you would have here maybe some initial conditions that are distributed according to this, but then maybe you kind of evolve according to some PDE ODE in this case, ODE system.
Okay. Yeah. Thanks a lot, Tim, for this interesting talk. And so if you come to Costa Rica, maybe we can arrange in-person talk. And
that would be nice.
Of course, it was very, very interesting, and thanks a lot for this talk.
Yeah, thank you for coming. So I mean, if anybody wants to chat more or so, you can also send me a message. I'll put my email address. I don't know if this is a good time for you to chat now. What is it? 12 now, right? Or half.
It's only 11:30, but yeah, maybe we can leave it here, and if someone else wants to write you an email or something like that, maybe he can get in contact with you.
Please feel free to contact me. Yeah, I'm happy to discuss. Also, I'm happy to hear what you're doing.
Okay.
All right.
Yeah. Thanks a lot, Tim.
Okay.
Bye. Muchas gracias. Hasta luego.
Muchas gracias.
Hasta luego. Muchas gracias.
Hasta luego. Muchas gracias.
Gracias.